Okay, so section 5.4 covers the fundamental theorem of calculus. And there are two parts to the fundamental theorem of calculus, and we're going to look at the first part. Okay, so in the first part, it's basically giving us a way to evaluate a definite integral by simply finding an antiderivative and then evaluating that antiderivative at b and a, which are the boundary of the interval from a to b. Okay, so here's the statement. So if cap f is an antiderivative of our function f, then computing this definite integral, which you can think of as area under a curve of f between a and b if f is a non-negative function, okay? Or more generally, we can think of just computing this just to compute it. It's a simple matter of finding the antiderivative f, cap f, and then evaluating at b, evaluating at a, and then subtracting the two. Okay, so let's look at an example. So let's say our example is, switch to green. So if we want to integrate from 0 to 3, x squared, we'll do 2x squared minus 5 dx. So to evaluate this definite integral, the first thing that we do is we find an antiderivative. Okay, so the antiderivative, and I'll show you the notation that we're going to use. So first let's find the antiderivative of this 2x squared term. So using power rule for integration, add 1 to the exponent, divide by that exponent, so we get a 2/3 x cubed, okay? And then minus 5, the antiderivative of a constant is that constant times x, okay? And, I mean, from the theorem, all we need is an antiderivative. And so usually we add c, but here we don't need to add c because all we need is one antiderivative, and the one that we choose is the one in which c is equal to 0. So then what I'm going to do is I'm going to put this in parentheses. I'm going to put this bar here. I'm going to put these, what are called the limits of integration, here and here. So this is the lower limit, 0 is the lower limit, 3 is the upper limit. Okay? And so to evaluate this definite integral, what I do is I first plug in 3, that this is the cap f of b part. So that's equal to 2/3 times 3 cubed minus 5 times 3. And then minus, and here I need to use parentheses, or I'll use a square bracket. And then now I do the f of a part. So that would be plugging 0 into this expression. So it's 2/3, 0 cubed. Of course, you know that this is going to be 0. I'm going to plug it in anyway. Okay. And then, so we just continue evaluating. And this equals, I mean, this part in square brackets will be 0. And this part here looks like we'll get 18 minus 15, or 3. Okay. So this is a way of evaluating a definite integral using fundamental theorem of calculus. And as I mentioned, these definite integrals arise from when we're trying to find area under a curve. Okay, so in this next example, we're going to look at the area under the curve e to the x. And we'll do that for, let's see, between 1 and 3. So I'll say, example, find the area under the curve y equals e to the x for x between 1 and 3. Okay? So, I mean, I can draw myself a picture. You know what e to the x, the exponential function, looks like? Okay, I'll mark off 1 here and 3 there. And this is not the scale, but to compute this area on the curve, okay, it's that area is equal to the integral from 1 to 3 of e to the x dx. Right? And here we're not going to approximate it with rectangles. We are just going to use this fundamental theorem of calculus to find this area. So the antiderivative in this case, very simple, just e to the x, right? And I'm going to put my bar here and put my limits of integration there, okay? And this just simply means to plug 3 in to our antiderivative, it's e cubed, and then subtract plugging 1 into our antiderivative, that would be equal to 1, okay? Or e. And so this I can simplify, if I'd like to, I can just factor out an e and write this as e times e squared minus 1. So this would be the area under that curve.